Begin when you're ready, please, Professor.
Okay. Oh, wait a minute. All righty. Let me go. Well, hello and welcome everyone to Learning from Home, and welcome to the Hewlett-Woodmere Public Library's profile of four cosmic mysteries. My name is Dr. Bill Thierfelder, and I'll be your host today. Now, for those of you who don't know me, I'm a retired professor of arts and humanities and docent emeritus from the American Museum of Natural History in New York. I live in Portland, Oregon, where I'm speaking to you from today, and where I'm an artist, writer, and lecturer. But I also return regularly to New York, where I continue my work at the museum and enjoy the wonders of the Big Apple. Now, everything that you're going to hear in this program today uses the web resources and books that you are about to see on my website. Uh, Stay tuned for that. But for this presentation, I especially use the following sources to build its structure and its script: Wikipedia and Britannica, the National Aeronautics and Space Administration, NASA, and the European Space Agency, SETI, the search for extraterrestrial intelligence, SETI, the Planetary Society, and space.com, a really terrific website. And I also used Live Science, Nat Geo, and Astronomy Magazine. Now, today, we're going to be looking at four mysteries that continue to challenge and often perplex scientists. Now, there are, of course, dozens more mysteries we could explore, but the following four have really gained a lot of traction in the last few years. Is there life beyond Earth? Scientists believe that we may discover microbial life on nearby worlds like Venus or Mars, and there's always the possibility that we may find advanced civilizations in other planetary systems around stars in our own galaxy or in the untold billions of galaxies that make up the universe. Dark matter and dark energy, they comprise nearly 95% of our universe. Well, what exactly are they, and how did they help the universe to unfold the way it has? And what role do they continue to play? Now, another area of serious scientific investigation is the possibility that our universe is actually one of many other universes, possibly numbering in the millions or more. Besides mainstream science, well, this concept is now one of the common tropes of science fiction. Just ask the patrons of Powell Books here in Portland, Oregon, or fans of Doctor Strange or Spider Man or many other Marvel comic heroes. And finally, we'll look at black holes and the supermassive versions that lie at the core of every galaxy in the known universe. Now, since we can't possibly cover all of those four topics in one presentation, I invite you to take a deeper dive on my website, makingwings.net. And in this case, it's deeper dive number 100. Now, let me demonstrate. So it's making wings, one word, .net. And you should be seeing that on your screen now. And if you go to that page, just click on the hamburger menu up here. They call it a hamburger menu because it's a stack. And you'll see a bunch of drop down items. Please feel free to visit any of them. But for our purposes, you're going to click on that little downward arrow next to Lecture Deep Dives. And once again, you're going to see oodles of things. Please feel free to visit any of these. These are presentations that I have given or will be giving in the near future. Now, today's is number 100, although you might find the 65-minute universe interesting, but specific to today is four cosmic mysteries. I also have a drop down about our solar system. Again, you might find that interesting, but today is number 100 for cosmic mysteries. And again, we're gonna focus on these four areas today. There are some recommended books. So when I mention them during the course of the presentation, you don't have to scamper for a paper and pencil. It's all here on the website. You can copy down titles and authors. I have some recommended streaming materials and DVD and Blu-ray materials. And then I go through each of the topics, life beyond Earth, with both print and video resources, dark matter and dark energy, print and video, the multiverse, you got it, print and video, and supermassive black holes, again, print and video. So there is, no pun intended here, a wealth of material, astronomical amount of material that you can look at. Makingwings.net, Deeper Dive 100, but there's also Deeper Dive 64 and a whole section on the solar system. So let's begin. One of the things that you just saw, suggested media. Brian Clegg's Dark Energy and Dark Matter, the hidden 95% of the universe, is a real good introduction to an understanding of this mysterious area of cosmology. The popular British physicist and musician Brian Cox and his collaborator, the physicist Jeff Forshaw, have written a very understandable study of black holes. Paul Halpern has tackled the topic of universes beyond our own in his book, The Allure of the Multiverse. And physicist James Trefil and planetary scientist Michael Summers pose the far-reaching question of what alien life might look like when humankind finds it. Their book is called Imagined Life. Very lively, very innovative, very accessible. Two other noteworthy books are Neil deGrasse Tyson's very engaging Death by Black Hole and Other Cosmic Quandaries, like that. DK Books, The Mysteries of the Universe, excellent too. DK, if you don't know it, is a British publisher that produces lavishly illustrated texts on numerous scientific topics and art projects. I mean, they just broad range of materials, but I particularly like their science book, and they can be enjoyed by both young readers as well as adults. And if you'd like some viewing pleasure, PBS has been broadcasting a remarkable science series called Nova since March of 1974. I thought it was March of 1972, so I'm gonna have to double check on it, but it's since the early 70s. And during we're now up to year 52, so I guess it'd be 1972, they broadcast close to 1,000 episodes, including The Universe Revealed, Black Hole Apocalypse, New Eye on the Universe, and Looking for Life on Mars. All very relevant to today's presentation. They're available on DVD, and they can also be streamed online. I would also recommend How the Universe Works, which has been broadcasting since 2010, first on Discovery Channel, now on the Science Channel. Any of the 95 episodes are terrific introductions, including the four that we're looking at today. And you can actually get a complete list of all the episodes on Wikipedia, and they can all be streamed as well. The History Channel's The Universe, which ran between 2007 and 2015, 88 episodes, 9 seasons, also very worthwhile, can also be streamed. The one caveat that I have with this series, and basically any book that we're looking at, or any DVD that you might look at is that once they're out there, they might become out not outdated, but there might be some tweaks in the information, sometimes within days or weeks. I mean, the the go words in science are stay tuned. So just keep that in mind. But all of these that I've just recommended, they have things that are really worthwhile. Well, with all of that said, time to dive in. And the first topic is life beyond Earth. Well, it's now generally accepted that every one of the 100 billion or more stars in our Milky Way galaxy, and the billions upon billions of stars in the 2 or 3 trillion, some people believe it's up to trillions of galaxies in the observable universe, have planets. In fact, that's the current wisdom, that every star has at least one planet. Now, to think that our world is the only one planet to have life out of the quadrillion planets in the universe is really quite ludicrous. I like to call it Homo sapiens hubris. But what do we mean by life? Well, according to current scientific understanding, the first life on Earth was microbial, meaning it consisted of microscopic organisms like bacteria and archaea, which left evidence of their existence in rocks dating back billions of years. Scientists have found fossilized microbial mats called stromatolites, which are layered structures created by ancient microbial communities, providing evidence of early microbial life. The oldest evidence of life on Earth is believed to be about 3.5 billion years old. So microbes have played a crucial role in shaping Earth's early environment and paved the way for the evolution of more complex life forms. Yeah, and so, when you look at a stromatolite, you're looking at your great, 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 great grandpa to the 99th power there. Now, all of this evidence leads astrobiologists to believe that a similar evolutionary event may have occurred on other planets throughout the universe. And by the way, stromatolites are still alive and well on planet Earth. This picture you see here are stromatolite mats that are growing off the western coast of Australia. So I guess you could make an argument that they are the oldest life forms on the planet, dating back 3.5 billion years. Now, within our own solar system, there is general consensus among mainstream scientists that intelligent life as we know it has never existed on Mars, unless they were visiting aliens. But there's nothing native born to Mars as far as we know. But there is strong evidence that microbial life existed there several billion years ago, before that small planet's core cooled and was unable to maintain a protective magnetic field or a thick atmosphere. So, in other words, over time, it lost its magnetic field and it lost its atmosphere. Just didn't have enough gravity, too small a planet to hold a thick atmosphere. Well, it did have oceans at one time, but before its oceans evaporated, some scientists guesstimate about 3 billion years ago, it is quite possible and even likely that microbial life existed there, evidence of which can be found in certain amino acids and other chemical signatures across the planet that all the Mars rovers have discovered. There seems to be evidence of microbe fossils in some Martian meteorites that have landed on Earth. In other words, an asteroid or a large meteorite hits Mars, fragments are blasted off into space, and some of those little fragments find their way to Earth. And lo and behold, we're able to look at them. And some scientists believe, as you can see in the lower right there, that those little strands that you see there might actually be the fossils of microbes. And there is also the possibility of microbial or bacterial mats on former seabeds in ancient sand dunes. I put a little yellow arrow there. That little white thing there could possibly be a bacterial mat, similar to a stromatolite. Meanwhile, though the surface of Venus is far too hot to support any kind of life as we know it, there is increasing evidence that microbial life might exist in the cooler regions of Venus's upper cloud cover. The detection of phosphine in Venus's atmosphere is a possible sign of life, but it is not yet conclusive proof. Phosphine is a toxic, colorless, smelly gas that is produced by life forms on Earth, primarily by microbes that live in oxygen free environments. Astronomers detected a light-based signature of phosphine in Venus's atmosphere, suggesting the possibility of microbial activity in the upper layers of the planet's atmosphere. Scientists have ruled out other possibilities for the source of that phosphine, such as volcanoes, lightning, meteorites, or other extreme scenarios. So, as we like to say in the world of science, stay tuned. Now, the massive rifts and cracks on the surface of Jupiter's moon Europa indicate a deep ocean below, and the reddish color along those cracks may be an indication of tholins, which are complex organic compounds that are made up of carbon, hydrogen, and nitrogen. So this is an actual photograph of the surface of Europa, and you can see these cracks that have formed in the ocean that lies underneath the moon Europa. And here's an artist's renditioning of that. And they're wondering if that could be tholins, the reddish color. You may find it yourself if you've ever done a deep cleaning of your bathroom tub or a sink. Sometimes you'll see that even after a few days, there might be a little bit of redness around the drain or something. Well, that basically is a tholene. Currently, NASA's Europa Clipper is on its way to Europa to determine whether there's life, microbial or otherwise, that exists in that globe-wide ocean beneath the moon's outer crust. And there are drawing board projects to send vehicles to conduct exploratory missions in that ocean at some point. Perhaps in the deep darkness, there are hydrothermal vents similar to those found in oceans on Earth that could support life. Moving away from our solar system, using massive telescopes on Earth, as well as new ones in deep space like the James Webb Telescope, scientists are now exploring planets around other stars. On your screen, you see the planets that orbit the red dwarf star TRAPPIST, which is about 41 light years away, meaning that the light from TRAPPIST that we are seeing on Earth today left TRAPPIST 41 years ago. Several of the planets in the TRAPPIST system, especially those lettered E, F, and G, are in the so-called habitable zone. That region is also known as the Goldilocks zone. It's an area around a star where temperatures are suitable for liquid water to exist on a planet's surface, which is considered a key factor for potential habitability. In the TRAPPIST system, these three planets are situated within this zone. Now, more recent observations suggest TRAPPIST C, D, and F might be more conducive to life. Regardless, what kind of life are we talking about? And again, these are planets that might have water. There may be whole life forms that don't need water, that live on sulfuric acid, for example. So, again, it's a stay tuned moment. Now, could the life on those planets, because we don't believe there's any intelligent or sentient life in our solar system except ours, but in other planets, on exoplanets, could there be intelligent life, a civilization? And is it a current civilization? For example, could intelligent life on one of the TRAPPIST planets have developed millions of years ago and gone extinct? If we were able to visit TRAPPIST E, for example, would we find ruins or other signs of a former civilization? And what about outside our galaxy? Well, there are trillions of galaxies in the universe, each holding billions of stars, and each one of those stars probably has a planetary system. Could intelligent life have lived on one of those planets long ago in a galaxy far, far away? Hmm. Well, what I'd like to do is spend the next 8 or so minutes exploring how scientists today are searching for evidence of intelligent life. Not just a few microbes, but actual technological intelligence. So I'm going to show you this video. You may have to adjust the sound on your devices. And as always the case with YouTube videos, you're going to find some errors in the closed captioning. But here we go. And okay, you should now be seeing on your screen something that says ancient contact. This is from the Bloomberg Group. For those of you who are art lovers, you know that Bloomberg now has wonderful tours of art museums and science museums. Well, Bloomberg also has a whole series of wonderful science videos, including this one. So enjoy.
There may be other intelligent civilizations capable of communicating with us. The impact on ourselves of contact with another intelligent civilization is now being discussed by serious thinkers the world over.
It seemed to me just perfectly natural that we would not be the only manifestation of life in the cosmos.
Out there is a million other civilizations, and they're all a lot smarter than us.
We now know without a doubt that the possibilities for life are literally innumerable.
And we haven't begun to look. We have way more places still to go.
So we take very large telescopes and we point them at nearby stars or nearby galaxies and look for that special kind of radio signal that we think is only produced by technology.
It's time to commit to finding the answer to search for life beyond Earth. We are alive, we are intelligent, we must know.
We are literally doing an experiment to find out what the answer is, rather than doing what we've done for millennia, which is to ask the priests and the philosophers what we should believe about life beyond Earth.
Dr. Jill Tarter is part of a movement known as SETI, the Search for Extraterrestrial Intelligence. She's dedicated her life to it. She's also the inspiration behind Jodie Foster's character in the sci-fi movie Contact.
So if it's just us, seems like an awful waste of space.
Today, SETI is a mission involving scientists from around the world.
So what SETI searches look for is electromagnetic radiation, like radio light, that is different than the radio signals that we get from natural objects like stars and galaxies and quasars, and consistent with the kind of light or electromagnetic radiation that's produced by technology.
Andrew Simeon heads up a team at Berkeley University.
We're up to 8.8 petabytes at Green Bank, right?
For 10 years, they'll be scanning the cosmos as part of a $100 million privately funded initiative.
Technological sources have a very interesting property, which is that they can compress electromagnetic energy in time or in frequency. So you can have a lot of energy, a lot of radio energy at just one place on the radio dial, and that's something that nature doesn't tend to do.
The team's work is the most comprehensive search ever undertaken in nearly 6 decades of SETI efforts. And technological advances mean that the search is finally building momentum.
What we've done for a number of years is to go to a large radio telescope, presumably a national facility, and rent time, or figure out a way to piggyback on other people's observations. And so we wanted to get to a situation where we were doing SETI 24/7.
290 miles northeast of San Francisco is the Allen Telescope, a cluster of small dishes dedicated in large part to SETI research.
The Allen Telescope Array is the first time we've ever built a large radio telescope out of a lot of small dishes. The joy of having small dishes is that they look at a large area on the sky all at once. Ultimately, we'd like to have 350 of these 6-meter dishes here. Right now, we have 42.
Alongside more telescopes, more powerful computers offer a chance to expand the search. The quantity of data produced is staggering.
With our next generation of radio telescopes, we'll be ingesting as much data from just one telescope as is coursing through the entire internet at any given second. So we collect a massive amount of data from the telescopes that we observe with, and some snippets of that data are actually brought back to our lab here at Berkeley. Like there's this gradual roll-off. We actually have to look for the sorts of signals that we're trying to find. And to do that, we develop powerful algorithms, including algorithms that use things like machine learning and artificial intelligence.
Scientists now know that most stars have planets. Jill Tarter believes this radically increases the chances life is out there.
When I was a graduate student, we knew about 9 planets, those in our solar system. But we didn't know about planets around other stars, not at all. Today we know that there are more planets out there than stars. Every star has, on average, at least 1 planet, and usually more. So that is a huge game changer. The universe seems a lot more potentially biofriendly, and now lots of people are interested in the question of life beyond Earth.
There are more stars than grains of sand on all the beaches of the world. If you look at one of these grains of sand and say that's the sun, and the third planet around it's habitable, and you look at the beach, I mean, how could it happen in one grain of sand and not in others? So we're very optimistic about SETI. It's probably just a matter of us being able to recognize what a very advanced civilization would look like.
Lawrence Doyle was part of the NASA team that used the Kepler Space Telescope to hunt for planets outside our solar system, but now he's bringing the search back down to Earth.
There are various kinds of intelligence, but the one that SETI is going to detect is going to be communication intelligence. Everything communicates. All animals and even plants communicate. It's just a matter of how complex is that communication. I thought, well, why aren't we studying non-human communication on Earth? So, as a proxy for an extraterrestrial signal, we proposed, starting with bottlenose dolphins and humpback whales and squirrel monkeys, to kind of design an intelligence filter for SETI so that we can recognize the general rules of intelligence. So we've devised various ways of looking at a signal, a message, and analyzing how complex, what the relationships are between signals. In human linguistics, the relationships are called syntax. If you're missing a word, you can recover it. If you're missing 2 words in a row, you can still recover. 3, you can see it gets harder. If you go up to 9, there's still a possibility you could fill in those words, but there's very low connection. If you're missing 10 words, you might as well just guess a word from the dictionary. So we go up to 9th order entropy. That is, there are still connections 9 words away of grammar and syntax. All animals, all people, all extraterrestrials, they have to follow these rules if they're transmitting knowledge to each other. And if and when we get a message, we can recognize the complexity of that communication system. We can say, okay, we go up to 9th order entropy, word entropy. Squirrel monkeys probably go up to 2nd order. Humpback whales, we don't know yet. We haven't got enough data. Extraterrestrial signal comes in and they go up to 20th order entropy. And we are going to know that their communication system is to ours as ours is to squirrel monkeys.
We are connected to this huge cosmos, and we want to know what else might have evolved out there.
Were we to know for sure that the universe actually many, many times has given rise to some sort of organism like us that thinks and asks questions about the universe itself, I think it could very much change our perspective on science and our perspective as humans. And I think the ultimate outcome of that change in perspective could be truly, truly amazing indeed.
Very cool. Close that down. And let's go here. Where am I? I'm here. There you go. Really cool little video. Really gives you a nice backdrop. I'd also like to pull a plug. I meant to put a picture of it on the screen, but some of you may be aware that the writer Andy Weir, who wrote the book The Martian, which was made into a wonderful film a few years back with Matt Damon. Well, he wrote a book about exactly this topic, about searching for intelligent life, called Project Hail Mary. Really cool. And it's coming out as a film this year, at some point later this year, with Ryan Gosling as the hero. So I recommend that. Now, I want to quickly add that in addition to the 42 radio telescopes in the Allen array, SETI now has access to the 28 telescopes at the Carl G. Jansky Very Large Array in Magdalena, New Mexico, along the Rio Grande River in the central part of the state. It's all very exciting stuff. So whether it's a microbe or a full-scale civilization, there's increasing belief that there's life out there, and we are on the hunt. Well, let's shift to another great mystery, dark matter and dark energy. Now, we know they exist, but we can't see them. Let's explore that. I want to show you this diagram. This is where we're going to start. It shows the spectrum of electromagnetic energy in the known universe. Electromagnetic energy refers to the energy carried by radio and microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. This energy is understood to be a stream of particles that's called photons. Now, essentially, photons are the building blocks of electromagnetic radiation, with different types of radiation distinguished by the energy level of their photons. Visible light represents only a small portion of the entire spectrum. Our eyes can't see the other kinds of photons. The other photons are detectable by specialized machinery and used by everything from radios to X-ray machines. But in general, everything that you see here helps to create for us our way to look at the visible universe, not just visible light, but all these other kinds of photons. Well, even more humbling is the fact that what you can see, whether it's with your eyes or special machinery, and what exists on the electromagnetic spectrum actually represents only 5% of what we can detect, either with our eyes or with scientific equipment, as I said. Now, the Institute of Physics puts it this way. Everything we see in the universe is only 5% of the whole universe. The rest of things are simply dark energy and dark matter. This makes us feel so insignificant now. Well, thank you, Institute of Physics, for giving us that remarkable, humbling idea. Now, we know that dark matter exists because of the gravitational effect it has on the visible universe. Those particles of dark matter are starting to receive names like axions, gravitons, neutralinos, and my favorite, WIMPs, which stands for a weakly interacting massive particle. By the way, WIMPs are the leading candidates for dark matter. The gravity of dark matter forms the tendrils of the web, visible clusters along these tendrils, creating what's called the cosmic web. So what we see is the visible universe, what you're seeing in this picture. That's just 5%. Another big chunk is the gravitational tug and pull of dark matter, and that's what causes these very wild tendrils. Now, the gravity of dark matter, as I say, forms, those clusters that form the universe. Well, if we step back far enough and get a bird's eye view, what you see on your screen is what you might see. And if you were to zoom in a little bit, each yellow blob in this artist's representation, you see, this little blob of light that you see represents one or more galaxies. And there are potentially trillions of galaxies in the visible universe. Now, as a sidebar, what I love about this image that I've just popped up on your screen and the other images that we've just looked at is that the universe actually looks like a living being, doesn't it? Nerves and synapses, veins and arteries. And indeed, there is very much another field of science which suggests that just as we are a living being, so is the universe a living being. And when you look at the universe, you're kind of getting proof of it. So there's something to tease your brain, right? Now, meanwhile, okay, so that's dark matter. Now, scientists believe that dark energy exists because observations of distant supernovas and galaxies reveal that the expansion of the universe is accelerating. And that indicates a mysterious force counteracting gravity, which would normally draw things together. Well, that force, this dark energy, is pushing galaxies apart. It's stretching out space-time as we know it. Well, what I'd like to do now is to show you this little 4.5 or so minute TED Ed talk that explains more. And once again, you may have to adjust the sound on your devices. Of course, for those of you who are familiar, live TED Talks, which can be 20 or so minutes, are great. But TED Ed Talks are usually between 4 and 6 minutes, and they're really great little nuggets of information, and they have the symbol TED Ed.
The ancient Greeks had a great idea. The universe is simple. In their minds, all you needed to make it were 4 elements: earth, air, fire, and water. As theories go, it's a beautiful one. It has simplicity and elegance. It says that by combining the 4 basic elements in different ways, you can produce all the wonderful diversity of the universe. Earth and fire, for example, give you things that are dry. Air and water, things that are wet. But as theories go, it had a problem. It didn't predict anything that could be measured. And measurement is the basis of experimental science. Worse still, the theory was wrong. But the Greeks were great scientists of the mind, and in the 5th century BC, Leucippus of Miletus came up with one of the most enduring scientific ideas ever. Everything we see is made up of tiny, indivisible bits of stuff called atoms. This theory is simple and elegant, and it has the advantage over the earth, air, fire, and water theory of being right. Centuries of scientific thought and experimentation have established that the real elements, things like hydrogen, carbon, and iron, can be broken down into atoms. In Leucippus's theory, the atom is the smallest indivisible bit of stuff that's still recognizable as hydrogen, carbon, or iron. The only thing wrong with Leucippus's idea is that atoms are, in fact, divisible. Furthermore, his atoms idea turns out to explain just a small part of what the universe is made of. What appears to be the ordinary stuff of the universe is in fact quite rare. Leucippus's atoms, and the things they're made of, actually make up only about 5% of what we know to be there. Physicists know the rest of the universe, 95% of it, as the dark universe, made of dark matter and dark energy. How do we know this? Well, we know because we look at things and we see them. That might seem rather simplistic, but it's actually quite profound. All the stuff that's made of atoms is visible. Light bounces off it and we can see it. When we look out into space, we see stars and galaxies. Some of them, like the one we live in, with beautiful spiral shapes spinning gracefully through space. When scientists first measured the motion of groups of galaxies in the 1930s and weighed the amount of matter they contained, they were in for a surprise. They found that there's not enough visible stuff in those groups to hold them together. Later measurements of individual galaxies confirmed this puzzling result. There's simply not enough visible stuff in galaxies to provide enough gravity to hold them together. From what we can see, they ought to fly apart, but they don't. So there must be stuff there that we can't see. We call that stuff dark matter. The best evidence for dark matter today comes from measurements of something called the cosmic microwave background, the afterglow of the Big Bang. But that's another story. All of the evidence we have says that dark matter is there and accounts for much of the stuff in those beautiful spiral galaxies that fill the heavens. So where does that leave us? We've long known that the heavens do not revolve around us, and that we're residents of a fairly ordinary planet orbiting a fairly ordinary star in a spiral arm of a fairly ordinary galaxy. The discovery of dark matter took us one step further away from the centre of things. It told us that the stuff we're made of is only a small fraction of what makes up the universe. But there was more to come. Early this century, scientists studying the outer reaches of the universe confirmed that not only is everything moving apart from everything else, as you'd expect in a universe that began in a hot, dense Big Bang, but that the universe's expansion also seems to be accelerating. What's that about? Either there's some kind of energy pushing this acceleration, just like you provide energy to accelerate a car, or gravity does not behave exactly as we think. Most scientists think it's the former, that there's some kind of energy driving the acceleration, and they've called it dark energy. Today's best measurements allow us to work out just how much of the universe is dark. It looks as if dark energy makes up about 68% of the universe, and dark matter about 27%, leaving just 5% for us, and everything else we can actually see. So what's the dark stuff made of? We don't know, but there's one theory called supersymmetry that could explain some of it. Supersymmetry, or SUSY for short, predicts a whole range of new particles, some of which could make up the dark matter. If we found evidence for SUSY, we could go from understanding 5% of our universe, the things we can actually see, to around a third. Not bad for a day's work. Dark energy will probably be harder to understand, but there are some speculative theories out there that might point the way. Among them are theories that go back to that first great idea of the ancient Greeks, the idea that we began with several minutes ago, the idea that the universe must be simple. These theories predict that there is just a single element from which all the universe's wonderful diversity stems, a vibrating string. The idea is that all the particles we know today are just different harmonics on the string. Unfortunately, string theories today are as yet untestable. But with so much of the universe waiting to be explored, the stakes are high. Does all this make you feel small? It shouldn't. Instead, you should marvel in the fact that, as far as we know, you are a member of the only species in the universe able even to begin to grasp its wonders, and you're living at the right time to see our understanding explode.
Okay, my goodness. Now, I won't even begin to describe string theory. But I'd like to take a quick look at something else the video mentioned, the cosmic microwave background, something that seems to prove the expansion of the universe, now believed to be caused by dark energy, but also a controversial topic that will lead into our third mystery. Stay tuned. The cosmic microwave background, also known as the CMB, is the faint microwave radiation that fills the observable universe and is considered the oldest light in the universe. The CMB is the leftover heat from the Big Bang, the beginning of the universe. The Big Bang theory states that the universe was very hot and expanding. And as it expanded, the gas cooled and produced a black body spectrum of photons. The discovery of the CMB in 1965 provided the first observational evidence supporting the Big Bang theory. The CMB is visible in all directions from Earth at a distance of 13.8 billion light years. This distance indicates the age of the universe, but it's not the true extent or width of the universe because space has been expanding ever since the Big Bang. What do I mean? Well, if you look at the diagram on the right, excuse me, it's on the left. You see the present marked with a yellow arrow. We are able to determine how far away objects are through spectral analysis and other kinds of measurements. The CMB is 13.8 billion light years away, and that means that the earliest light that we can see traveling at the speed of light has taken 13.8 billion years to reach us. But during those 13.8 billion years, the universe was and is still expanding. So based on current observations, rather than being 27.6 billion light years across, scientists have been able to determine that the universe is actually probably at least 93 billion light years in width, containing at least 2 trillion galaxies. Amazing and mind-boggling. But let's get back to the cosmic microwave background. One of the things that scientists have noted in the CMB is that certain patterns appeared, indicated by the warm reds and cold blues that you see on the map on your screen. That appear to show the distribution of energy and primitive structures in the very early universe. But it also seems to show mysterious cold spots like the one indicated on the screen. There are some theorists and scientists who suggest this may be where our early universe, for lack of a better word, bumped into another universe. And that tantalizing possibility brings us directly to our third mystery, the multiverse. So, what is the multiverse? It is a term that scientists use to describe the theory that beyond our observable universe, other universes may exist as well. These universes may have been created at the same time as ours, or perhaps more likely, they appeared at different times, perhaps through their own version of a Big Bang. And these universes travel through space-time in the same way that soap bubbles can float through the air, sometimes even touching. Now, one possibility that scientists are exploring is that these multiple universes are parallel, meaning that in every universe, there's another Earth, another you, another moon, another Mars, and so on. And in some of those universes, you might not even exist. It's truly everything, everywhere, all at once. Indeed, it's likely that parallel universes are not identical to our own at all. Most scientists believe that if there are multiple universes, each universe in the multiverse is different. Each universe has its own law of physics, which could be different from our own. For example, in one universe, light might not exist as we know it, or electrons might not exist or be different. Different universes could have different dimensional structures, which could mean different ways to view space and time. And different universes could have different particle types. Bottom line, even if we could reach another universe, it could be very different from our own. So let's explore some more. This is a little video from PBS's wonderful show that we've spoken of earlier called Nova. And again, you may have to adjust the sound on your devices. have to wait till it hooks in completely here. Okay, I'm going to make sure it's at the beginning. I'm going to make sure closed captioning, and here we go, from Nova.
We usually think of our universe as a vast, nearly endless expanse that contains every galaxy, star, and atom in existence. But is it? What if our universe is just one of many? Could we live in a multiverse? One with parallel universes containing other galaxies and possibly other Earths? This isn't just the stuff of science fiction. Physicists are starting to take the multiverse idea pretty seriously. Here are 4 real models of what parallel universes might look like and how they could form. The inflationary multiverse. You know how you learned in school that the universe started with the Big Bang? Well, what if that Big Bang wasn't the only one? In the inflationary multiverse model, Big Bangs are happening all the time. The idea is that there's an endless sea of energy where universes pop up like bubbles in the ocean. Each new bubble universe is created during a rapid period of expansion called inflation. In these other universes, the physics could be strangely different. There could be universes where gravity is weak and objects seem to almost float around, or universes where electromagnetism is strikingly different. The quilted multiverse. In this model, there's really just one universe, but it's not just big, it's truly infinite. So infinite that if you could search through the infinite space, search the infinite galaxies with infinite stars, you'd eventually find a number of planet Earths, just like our own. And on some of those Earths, you'd even find someone identical to you. But you aren't likely to ever meet yourself, because that other you probably lives in an unreachable patch in our infinite cosmic quilt. Even if you started flying through space at light speed right after the universe was born, while you could travel tens of billions of light years away, you could never escape your small local patch in the endless quilt of space. The quantum multiverse. When things get really small, they get really weird. Quantum mechanics rules the behavior of small particles, like this electron. As it moves along, where exactly is it? Quantum mechanics would say that it could be any number of places. But take a picture. It's right there. But how did it decide where to go when you took the picture? In the quantum multiverse hypothesis, fickle particles don't have to decide where to pose for pictures. Each of those possibilities would live in its own universe. And the crazy thing is that anytime you take a picture or observe something, you split the universe. You can't see all the universes because you just live in one of the many possibilities. So as you move along your life observing particles, people, puppies, the universe is constantly splitting, and you're just traveling along one of the many paths in the quantum multiverse. The brain multiverse. Sometimes people talk of parallel universes as alternate dimensions. We live in 3 spatial dimensions, front to back, side to side, and down to up. Are there more dimensions though? In the brain multiverse, the answer is yes, because the brain multiverse comes out of a type of string theory where our 3-dimensional universe lives on a membrane, or brain for short, that is actually embedded in 10 dimensions. But our brain wouldn't be the only one. There could be other brains with other universes. It's like how a 3-dimensional book has many 2-dimensional pages, but our multiverse book is 10-dimensional, and our universe is on one of the many 3-dimensional pages. So is there any hard evidence that any of these 4 multiverses exist? Scientists working on a telescope called BICEP 2 think they've observed in the sky a sort of fingerprint left over from just after the Big Bang. It's a pattern of polarized light resulting from our universe's brief period of rapid expansion called inflation. So if inflation happened here, it could have happened elsewhere too, implying the existence of a vast inflationary multiverse. One with endless bubbling universes, each with its very own Big Bang, and inside, they're probably infinitely big, which is evidence that the quilted multiverse may also be possible. Right now there's no evidence for the other 2 multiverses, the brain and quantum multiverses, but maybe one day. So the next time you look up at the sky, just remember that what you're seeing may just be a patch in a bubble in an endless multiverse.
Okay. Did that make you feel unusually small and insignificant? Remarkable stuff. But before we move on, I spoke about the wonky subtitles, right? You may have noticed in the closed captions that they spelled brain Brain, and that's incorrect. Okay. The correct spelling is indeed brain, which is a contraction of the word membrane. The brain universe theory is a branch of string theory, which is way beyond my dominant right brain capabilities. And the bottom line is that there may be infinite possibilities in the brain universe, many random and based on chance. It's quite a beautiful concept, and I wish I had the left brain math skills to understand it. But all of these things do bring us back to our final mystery, and that's supermassive black holes. So whether it's one universe or a multiverse, if they contain galaxies, it's quite possible they all have at their core a supermassive black hole. It's possible. Well, our universe contains at least 2 trillion galaxies. That's a very good guesstimate, which in turn are made up of billions of stars. And at the center of each of these galaxies, including our Milky Way, is a black hole so enormous that scientists call them supermassive black holes. The illustration on your screen shows actually what can happen is that sometimes black holes are floating along and then they merge and get bigger and bigger and bigger and bigger. And that's one way you get a supermassive black hole, but more of that in a moment. So what exactly is a black hole? According to NASA, a black hole is a place in space where gravity pulls so much that even light cannot get out. The gravity is so strong because matter has been squeezed into a tiny space. This can happen when a star is dying because no light can get out. People can't see the black holes. Okay. So that's what NASA says. So here we see 2 possibilities regarding the life of a star. All stars form from inside clouds of gas that are called nebulas. And you see that on the left of your screen. Now, where the split happens is that you can get basically 2 different kinds of stars. All stars form inside clouds of gas, right? And the top row, you see that stars like our sun over the course of billions of years use up their hydrogen and become a red giant. At some point, the material that's left collapses into a white dwarf. That's what's going to happen to the sun. That's the top row. Now look at the bottom row. And along the bottom, you see that some larger stars will eventually grow into super red giants and eventually explode into massive supernovas. The material that will be left over from the supernova will either collapse into a very dense neutron star, which you see over here, or will collapse into something even denser, and that's a black hole. Now, here's the structure of a black hole. Supermassive black holes are structured pretty much the same way. At the center is the singularity, the place where there's so much gravity that not even light can escape. The event horizon around a singularity is the place where matter and energy cannot escape. It is the point of no return, and this is the black part of the black hole. The accretion disk is a disk of superheated gas and dust that whirls around the event horizon at immense speeds. you have jets of particles and radiation that blast out from the north and the south poles of the black hole. It's not from the interior of the black hole, it's from the gases that are circling the black hole, and they just become so compressed they just shoot out as these remarkable jets. Other structures include the photon sphere and the innermost stable orbit. That completes the structure of black holes. Now, the size of a black hole can vary from just a few miles wide to millions of miles across, depending on its mass. And some scientists are trying to work in labs here on Earth to actually create little mini black holes that are only like an inch or so across or less. But supermassive black holes, on the other hand, can range in size from millions to hundreds of billions of miles across, depending on their mass, with some of the largest reaching diameters of over 260 billion miles across. So just as planets orbit a star, so all the stars orbit the supermassive black hole at the center of a galaxy. Now, black holes are very hungry beasts. They suck up other stars and, as I showed you in the first illustration, even other black holes. And that's how some scientists believe that supermassive black holes form. They devour not only stars, but other black holes, and they simply become larger and larger and larger. Basically, they're gorging. Now, what you see on your screen, this is the first picture of a black hole taken in 2019. Using the Event Horizon Telescope, scientists obtained an image of the supermassive black hole at the center of galaxy M87, which is located 55 million light years away from Earth, meaning that the light from that galaxy took 55 million years to get here. The Event Horizon Telescope, the EHT, is a telescope array that consists of a global network of radio telescopes. They're spread all over the planet, Australia, South America, Southern Africa, etc. And then in May of 2022, the photo of the supermassive black hole at the center of our own Milky Way, known as Sagittarius A star, shows a ring-like structure with a dark central region. Essentially, that's that area where the black hole actually is. It's surrounded by that ring of glowing gas. The image was also captured by the Event Horizon Telescope. This image represents the first direct visual evidence of the supermassive black hole at the center of our galaxy, the Milky Way. Well, let's learn a little more about these remarkable structures. Here's a little 3-minute video from the National Geographic. National Geographic creates these wonderful little videos called Science 101. And there are varieties of topics. And in this case, black holes 101. It's really cool. And by the way, all the 4 videos that we have watched today, this being the 4th, I have links for them on my website in case you want to rewatch, pause, stop, learn, take notes, whatever.
Black holes are among the most fascinating objects in our universe, and also the most mysterious. A black hole is a region in space where the force of gravity is so strong, not even light, the fastest known entity in our universe, can escape. The boundary of a black hole is called the event horizon, a point of no return beyond which we truly cannot see. Once something crosses the event horizon, it collapses into the black hole's singularity, an infinitely small, infinitely dense point where space, time, and the laws of physics no longer apply. Scientists have theorized several different types of black holes, with stellar and supermassive black holes being the most common. Stellar black holes form when massive stars die and collapse. They're roughly 10 to 20 times the mass of our sun and scattered throughout the universe. There could be millions of these stellar black holes in the Milky Way alone. Supermassive black holes are giants by comparison, measuring millions, even billions of times more massive than our sun. Scientists can only guess how they form, but we do know they exist at the center of just about every large galaxy, including our own. Sagittarius A, the supermassive black hole at the center of the Milky Way, has a mass of roughly 4 million suns and has a diameter about the distance between the Earth and our sun. Because black holes are invisible, the only way for scientists to detect and study them is to observe their effect on nearby matter. This includes accretion disks, a disk of particles that form when gases and dust fall toward a black hole, and quasars, jets of particles that blast out of supermassive black holes. Black holes remained largely unknown until the 20th century. In 1916, using Einstein's general theory of relativity, a German physicist named Karl Schwarzschild calculated that any mass could become a black hole if it were compressed tightly enough. But it wasn't until 1971 when theory became reality. Astronomers studying the constellation Cygnus discovered the first black hole. An untold number of black holes are scattered throughout the universe, constantly warping space and time, altering entire galaxies, and endlessly inspiring both scientists and our collective imagination.
Indeed, and they certainly inspire our imaginations too. Needless to say, the supermassive black hole at the center of all galaxies, that's kind of the hub. All the stars in a galaxy circle those black holes, those supermassive black holes. So without a supermassive black hole and dark matter, galaxies might just fall apart. So we need our black holes and we need our dark matter. Well, whoo, there you have it. I've thrown a lot of stuff at you in the last hour. 4 of the great mysteries of the universe that challenge us. Are we alone in that vast cosmos? Is there life beyond our little blue marble in space, as Carl Sagan said? What is dark matter and dark energy? How do they affect the universe in which we live? Is there such a thing as the multiverse? Are there parallel Earths? Is there another you or me out there living an alternate life in an alternate timeline? And how about black holes and the supermassive black holes at the center of all galaxies? How they control basically the destiny not only of that galaxy, but in essence, the universe. Man, all of this is mind-boggling and totally fascinating. So thank you for sticking with it. Thanks for being here today. I hope this program sparked your imagination. And remember, if you'd like to learn more, please visit my website, makingwings.net, and take deeper dive number 100. And again, you can also visit number 64 and also the one that's called Solar System. So now, before we talk about our next program, which is coming up